Hi, and welcome to NASA's Jet Propulsion Laboratory in Pasadena, California, and our special Facebook Live event devoted to NASA's Cassini mission to Saturn and its ring-grazing orbits. I'm Preston Dykes, and we've got a treat for you guys today because we're going to take your questions live from inside the Mission Control Center here at JPL. So let's go do that. This is a pretty special place, and we're pretty excited to bring you inside because it's not on the standard public tour to actually come down on the floor of the Mission Control Center. And actually, some of you who are big space fans will recognize this room. It's a place where you see people wearing identical polo shirts jumping up and down when we do something great like land a rover on Mars. Or there was that special evening in 2004 when the Cassini spacecraft fired its main rocket engine and slipped into orbit around Saturn. Cassini's been there ever since, studying the rings, the moons, the planet, and its magnetosphere, and revolutionizing our understanding of the Saturn system. And so here we are. This is mission control for JPL. This is the nerve center, or the communications hub for the communicating with the Deep Space Network, which is the system we use to talk to all of our spacecraft that are exploring the planets beyond the moon. And one of those is, of course, Cassini. And so today we're going to introduce you to two of the remarkable people who actually really work on Cassini. So one of them is right over here. Let's go meet her. Her name is Molly Bittner, and Molly is a mission planner on Cassini. How you doing, Molly?
Good, Preston. How are you? Thanks for coming.
Thank you for being here.
Of course.
I'm geeking out over this. I cannot stop. The view here is tremendous. This is a real-time simulation of what we would see if we were riding along next to Cassini at Saturn right now. This is a simulation, an application we call Eyes on the Solar System. You can download it and run this exact view yourself. Go to eyes.nasa.gov. So Molly, this is so cool. Can you tell us what we're seeing here? What's Cassini doing right now, and how does that fit into this kind of diagram thing I'm seeing over here?
Yeah, Preston, that's right. This application is really cool. It has a full model of the spacecraft and a full model of the Saturnian system. So right now, the reason why we're doing it at this point in time is the spacecraft is flying through the outer edges of the rings. As you can see in that picture right now, you can see the rings and the spacecraft flying on the outer edges. So that's what's great about this, is it shows the orientation of the spacecraft and the orientation of the entire Saturnian system right now.
So cool. And so that is part of this diagram we're seeing right here. These are a bunch of orbits of Cassini, right?
That's exactly right. So these are what's called the F-ring orbits. Those are shown in gray on this diagram up here. And so these gray F-ring orbits set up for these blue proximal orbits, and the last orange one is the final plunge into Saturn. So we're currently in these gray F-ring orbits grazing the outer edges of those rings, as you can see in that diagram.
And we like to call, we have different names for everything. We call the F-ring orbits are also the ring-grazing orbits. The blue proximal orbits, we found a cooler name to call them the grand finale orbits. We thought that sounded even cooler. So the reason why we're doing all this is the same motivation as everything we do on Cassini, and that's the science. And one of the best people I know to talk to about the science of Cassini is the mission's project scientist, Linda Spilker. Hey, Linda, how you doing?
Just fine, Preston. How you doing?
Awesome. Thank you for being here.
Happy to be here on this momentous occasion of actually plunging next to the rings.
So that's going on right now.
Right now, we're going close to the outer edge of the rings. Right now.
If you were to project yourself to Saturn right now, that's what you would see. So can you tell us a little bit about the science we're able to get from these unique ring-grazing orbits, and maybe talk a bit about what we've been able to see so far?
Well, this is the first time we've pulled the Cassini orbit very close to the outer edge of the rings, the closest ever. When we do that, we get excellent views of these tiny ring moons that are very close to the outer edge of the rings, and also of the outermost part of the rings itself. Views that we haven't seen since Saturn orbit insertion. In fact, let me share with you a couple of the remarkable images that have come back. This first one is of a tiny moon named Pandora. Pandora is about 50 kilometers across, and it's one of two shepherds on either side of Saturn's narrow F-ring. That's the last ring out of the main rings. You can see a large crater with white material. Maybe that's the fresh, icy snow underneath the coating of F-ring particles. This is an image of tiny Daphnis. Daphnis is only about 8 kilometers across, and Daphnis's gravity is opening up a gap called the Keeler Gap in Saturn's rings. Daphnis also creates a wave, just like the wake behind a motorboat. One part of the wave you can see is behind Daphnis, and out of this picture is the other piece of the wake. So just amazing. And the high resolution and the detail, like I say, that we haven't seen since those ring pictures back in 2004. And this picture is a series of pictures just released today. It's a picture of the edge of the B ring. You can see in the bright region those streaks. Some of the largest B ring particles create the streaks in the long exposures. Also, the ring particles don't just sort of hang out by themselves. They clump together and form these long structures. And so you're seeing some of this straw, is what we've nicknamed it, in the outer part of the B ring. Now, if you look carefully, Preston, you can see all these speckles, and those are just cosmic ray hits and blemishes. We're releasing the raw images so you can see along with us the very best resolution.
That is so cool that we're seeing the rings at such high resolution. Like, you know, it brings back memories of, you know, of arriving at Saturn.
Oh, of that night in 2004 where we first saw straw. Just gives me goosebumps.
Incredible. So if you're just joining us, we are here at the Jet Propulsion Laboratory, NASA JPL, and Mission Control, taking your questions about the ring grazing orbits of the Cassini mission at Saturn. And actually, we're going to do that now. We're going to take a question here. This is from Sanket Indy, who asks, how did you prepare the map for the expedition of Saturn? And I think what Sanket means, I hope, Molly, I think that's a good one for you. How did you plan that trajectory that we saw mapped out for Cassini probably way in advance?
Yeah, that's a great question. So these things are actually planned way in advance, just like you said. We plan out these trajectories with our navigation team, and we have another team, the spacecraft team, that plans the orientation of the spacecraft. So these two together, the navigation team creates this map, the path we follow, and then the spacecraft team really controls the spacecraft, where it points, where it looks, the amount of power, the amount of fuel in the spacecraft. And one of the interesting things in doing this is, how do we control the spacecraft as it's going through these dusty areas? How do we protect the spacecraft's delicate instruments, delicate line feed, such as the fuel? So this is a picture of our spacecraft, and not shown here, there's actually a cover over these main engines at the bottom, and we don't want dust particles getting into those engines because it would clog up those lines. So we actually close that cover when we go through dusty areas. So that's one of the cool things we do. And if it's really, really dusty, we'll even use this antenna as a shield. So the spacecraft flies through the rings, and that's blocking it and protecting all of our delicate science instruments.
It's a great shield.
And we've done that before, right? We did that when we arrived at Saturn II. We used the antenna that way, right?
We use it several times.
Okay.
Yep.
So that kind of leads to another question that we had from Brett Jensen, who asks, what's the average particle size and density in the areas Cassini will be passing through? Linda, you're a ring expert, so time to earn your stripes.
Right. Well, where we're passing just outside the rings, the particles are very small and very tenuous, probably only a few microns in size, like little tiny dust particles you might see in the sunlight if you looked toward the sun. And we don't have to worry about it. They're far apart. They're probably coming off the edge of the F-ring, and so we could hear them hitting the spacecraft. We've actually made little sound files, but we don't have to worry because they're so small and they won't hurt Cassini.
So let me follow up. This is a question from Sith Mal France, I guess a fellow Star Wars fan. If Cassini is taking samples of ring particles on its flybys, is it leaving a hole in the rings? And I guess it's not going through the rings, but it's going through like the ring plane, right?
Right, it's going through the plane of the rings, and yes, but the Cassini's footprint is so tiny. You know, this high gain antenna is only about 4 meters across, so it's just maybe making a very tiny hole in the very tenuous ring particles.
And then one more here. Sarah Marchand asks, so are you close enough to get images yet still avoid getting hit with particles? How close can you get? I think that's the one we haven't answered yet, is how close do we dare? And I think maybe both of you probably want to get real close.
Right,
and you probably say,
Yeah, it's always a trade we have to do, because the navigation team, you know, how close we get to any body affects our trajectory, right? The pull of gravity always affects everything we do. How close we get to those particles affects everything. So it's always a back and forth between the engineering team and the science team. We really want to set them up so they can have the maximum view of whatever they want to see, but we also want to protect the spacecraft at the same time. So we try to work together as much as possible to have the best view for them.
Right, and we figure out where does the particle density fall off enough that Cassini would be safe to fly through the ring. So we're a few thousand kilometers outside the F-ring. There's the narrow F-ring, and then the A-ring starts, and then the main rings after that. So we picked a place we felt very comfortable flying.
have another really good rings question for you, Linda. Evan Twyford asks, can you explain why the waves around Daphnis, on both sides of Daphnis, are moving in both directions? Do the rings move in different directions there?
Right. Well, the rings, you can think of the rings kind of like the solar system. The ring particles closest to Saturn move faster, and they can go around maybe in just 4 or 5 hours. The outer part of the ring, much more slowly, maybe 14 hours to go around once. So Daphnis, what happens is if you were riding along on Daphnis, the particles closer to Saturn would appear to be passing you up like horses on a racetrack. And then the particles to the outside of you are going more slowly. So that's why the wakes go both in front of you for the particles going faster and behind you for the particles that are moving more slowly.
Excellent. So a lot of folks have asked us, and this is kind of a general question, you know, you talked about setting up the grand finale, those blue orbits we saw earlier, setting up the end of the mission, though. We're headed toward the end. A lot of people want to know why are we doing that to begin with? Why the spacecraft's beautiful, it's healthy, it's discovering things. Now, I think I've heard before that it has something to do with the gas gauge being on empty, Molly?
Yeah, we're running a little bit low, Preston, unfortunately. So we have such a low amount of fuel left that we've carefully planned out all of our remaining maneuvers to use all that little bit of fuel very precisely. So we've planned out our maneuvers to use the main engine for some maneuvers and to use the RCS control systems, which uses a different set of fuel for other burns.
What's the RCS control system?
Reaction control system.
What is that?
They're thrusters. So they use hydrazine fuel instead of the monomethyl hydrazine that the other ones use.
Gotcha. Okay. So let's see. We've got a question here on the hexagon. You want to talk about the hexagon, Linda? What explains the hexagon? That was from Cameron Davis.
Right. The hexagon is a 6-sided jet stream at the North Pole of Saturn. It's about 2 Earth diameters in size, so it's huge. What's interesting is it's been there since Voyager flew by in the 1980s. And why it keeps its 6 sides, it's the only structure, the only hexagon in the solar system rotating around in the atmosphere. We don't know why it keeps its hexagonal shape. And from the F-ring orbits, we're going to get some really nice views down on the hexagon, movies, watching it in action. And inside of it, there's a hurricane right at the center, and also the aurora. So lots going on around the hexagon.
It's kind of fascinating. People are fascinated with the idea that there's this polygon, this weird shape there on a planet. It's very strange.
In an atmosphere.
In an atmosphere.
Yeah.
Here's a lovely question. This is from, I think, a little girl who's 5 years old, named Wyatt, from her dad. He said she wants to know, can you touch the rings like a wall?
Ooh, could you touch the rings like a wall? Most places you could probably just move your hand through the rings because the particles are so far apart. But in the B ring, the rings on average are only about 10 feet thick. In the B ring, it looks like the particles might be shoulder to shoulder. So maybe you could reach down and maybe touch ring particles. It wouldn't be like a wall because you could probably push them out of the way, but they'd be very close together in the B ring.
So I've got a question for you, Molly. It's just you know, people always want to know what are you most concerned about? Like if you're flying toward, if you're turning the spacecraft around. Linda was talking about tiny little particles. Are there particles out there that are big enough to hurt Cassini?
There actually are. So the mission planning team does a fluent study that uses some of the science instruments to actually measure the dust particles like Linda talked about. And if they're a small enough size, they can actually get in the fuel lines like I talked about earlier. And so we do that study for every ring crossing. And we're actually carrying on this new plan going forward where every ring that we cross through, we do these measurements again to really determine as we're going through these intense orbits, do we need to change our plan? Do we need to reorient the spacecraft? Is it necessary just to close the main engine cover, or do we really need to use the antenna as a shield? And so that's something that we're constantly updating in this process, and we're always learning new things.
So let's see, Linda, Frank Fizzle asks how many rings there are. I mean, it looks like there's an infinite number from this picture.
Right. If you look at the images of Saturn's rings, it looks like there are thousands of individual rings. But actually, there's very few places where there's space in between. So this, in a sense, is kind of like an optical illusion. They're just places where the ring particles are more dense, and they make a structure and then less dense, and just a very few gaps inside of the rings themselves. But it does kind of remind me of those grooves on a phonograph record, for those of you who remember those records.
So I want to remind folks where we are. We're at the Mission Control Center here at NASA JPL, the Jet Propulsion Laboratory, talking about the ring grazing orbits of our Cassini mission that's exploring Saturn. We're taking your questions. So let's see, I had a kind of an interesting one here. It was coming in. Wilhelm Sukan says, if I were to fly into the rings, what would they look like? We've talked about the scale, we've talked about how many they are, we've talked about the size of there's different ring particle sizes, but what would you see, Linda?
Right, if you could hold a ring particle in your hand, what might it look like? Well, it might look like a fluffy snowball with very fluffy, tiny particles on the outside, but maybe there's an icy, rocky core on the inside. But most of them are really small. Some of them the size of dust particles or like little hail particles, a few of them snowball-sized, and then a very few maybe even mountain-sized.
Cool, so let's see. Maybe both of you can answer this. James Roy Green asks, can you turn the spacecraft around so you can see Earth again before the end of the mission?
That's a great question. Yeah, so we actually turn to Earth a lot. That's how we communicate with the spacecraft. So this antenna isn't just a shield, it's actually an antenna, so we can communicate with the Earth. So we have antennas on the spacecraft, we also have antennas at the Earth. So there's pictures up here of 3 different stations that are located around the Earth. There's one in California, one in Spain, and one in Australia. And when we turn the spacecraft to Earth point, that's actually when we can communicate with the spacecraft. We can downlink data and receive data from the spacecraft, or we can send up commands so that they're loaded onto the spacecraft so it can turn around as much as they want. So we turn to Earth a lot, actually.
Right, but as far as taking pictures of the Earth, that's much harder to do. And we've done that for the last time before these ring grazing orbits. You have to get at a special orientation where Cassini is in a place that Saturn covers up the sun. Then you can look close enough to Saturn and not damage our sensitive cameras and get pictures. In fact, we have this beautiful mosaic, one of my favorite pictures, that if you look carefully, there's the Earth and the Moon, and then Mars and Venus, all in this same mosaic of pictures.
That's a really great picture. It's one of my favorites, yeah.
Probably one of our most famous from the whole mission. Here's a good one for you, Molly. Nick Garcia asks, what kind of temperatures does Cassini have to endure on the mission?
Oh, wow. It's cold at Saturn, let me just tell you that. So Saturn's a very cold place, and one of the things that's involved on the spacecraft team is we have all these subsystems, right? So there's a thermal subsystem that actually studies all of these temperatures, and they have heaters, they have all these blankets that are on the spacecraft that's really to protect our instruments, because everything there is frozen. So water there would be frozen, so it's cold.
But inside the spacecraft, is it just as cold, or do you warm it up?
No, so all of that thermal control subsystem, it's meant to keep the spacecraft warm. It keeps it within something called an AFT, an allowable flight temperature. So that's something we study at engineering. So we study, while we're designing spacecrafts, what temperatures are these going to operate under, and how do we keep a spacecraft in an allowable range so that those science instruments function properly once we're in this new environment.
And Molly, don't we have to keep the fuel lines warm before we use them, because you wouldn't want little bullets of ice coming out?
That's another great point. So we have these commands that actually turn on the heaters for the line. So when we fire the engines, the fuel's ready to go through. That's a good point.
So a couple of people are asking on Facebook, Linda, Catherine, John, they're asking about the origins of the rings. Do we know where they came from? Have we still not figured that out after 13 years? One person is asking, are they the remnants of a moon that got smashed? Is that something you guys have thought about?
Right. There are 2 possible ideas for how the rings might have formed. One is perhaps a comet or a moon got in too close to Saturn, torn apart by Saturn's gravity, and formed the ring. Another one is maybe the rings formed at the same time as Saturn from the leftover gas and dust that formed the planet. And Cassini's end of mission, we're going to get the mass of the rings. And if they're less massive than we think, then it's probably a moon or comet. More massive, maybe they formed as long ago as Saturn.
So another question to follow that up on, this is Catherine Garces, is saying, is the number of rings constant? She says, are some of them disappearing, or does the number remain the same? And that goes to the heart of something we've seen with Cassini. We've seen them changing before our eyes.
Right. Some of the rings, like the F ring, changes before our eyes. It changes its structure. But at the other rings, it's a remarkable, that detailed structure, how it's remained the same, except for these waves that move through the rings.
Gotcha. So let's see. Spencer Robertson Branting is saying, with all the ring particles bumping and bouncing off each other, do the rings build up some sort of electrical charge in the magnetic field?
That's an interesting question. It's possible that they do build up a charge, and maybe that's what makes these spokes, these particles that lift up above, when they come out of Saturn's shadow, they look like fingers. We only saw them when the rings were almost edge on to the sun. But there could be a charge on the rings. There could be like a tenuous ring atmosphere. Maybe some of those little molecules, like of water, which the rings are mostly made of, come off and make a very tenuous atmosphere, and maybe that atmosphere waters Saturn. So maybe some of the ring water is going to Saturn.
So Molly, Simon Farrell is asking, how long is the lag time between input and the craft actually moving?
That's a great question. So earlier when I was talking about the antennas and communicating with Earth, it's important to note that it takes light an hour and a half to travel from the Earth to Saturn. So that means it takes 3 hours for us to hear back. So we send a command, it takes an hour to get from Earth to Saturn, and then it takes another hour to receive that data back. And so whenever we're doing maneuvers, when we're firing these engines on the spacecraft, we literally have to sit 3 hours in silence to see what happened and to see if it was successful. And that was especially important as we were monitoring the fuel levels, because there's been some big maneuvers where we literally had to hold our breath, wait for 3 hours, and then see what happened.
And in fact, that's what we do right here, right? This little station says Cassini Mission ACE. And so maybe one of you can tell us what the ACE does or what we do here. This is where we talk to Cassini, right? Basically.
Yeah, so the scientists and the engineers both talk to the ACE. So the ACE is like the last point of command until commands are sent. So we have engineering commands that go up, we have science commands that go up, and so I'm in my office back there talking to the ACE. The ACE queues up commands, sends them up to the spacecraft, and then the ACE is also the first person to see the data when it comes back down, and it filters off to the scientists.
Great chair to be in.
Because I noticed there's no joystick. You actually fly it with a like a video.
That would be really fun if we did.
Yeah.
But it's really just a sequence of commands that we load up onto the spacecraft, and it executes those commands in time order at the time specified on the spacecraft.
Because it's a robot. It does what
Right. Yeah, in fact, maybe we send up 10 weeks of commands, fill up that computer memory, and then those commands point Cassini for 10 weeks, and then we send up another 10 weeks of commands.
Exactly right.
Well, here's a question about the planet itself. Saturn, I think we were surprised to find that in some ways the moons turned out to be some of the most interesting things with Cassini. But Tina wants to know, what have we learned already from these missions from Cassini about the interior of Saturn itself? Is it still a mystery?
There's a lot about Saturn's interior that's still a mystery, and we're going to sort of open up Saturn when we go into these grand finale orbits at the end of the mission. It's mostly a giant gas ball made mostly of hydrogen. We know it has a magnetic field, but where inside of Saturn does the magnetic field come from? Is there a rocky core about the size of the Earth? Lots of questions about the inside of Saturn. We haven't gotten quite close enough, like Juno is getting very close to Jupiter. In the same way at the end of the Cassini mission, we'll do that for Saturn too.
Okay, another rings question here. Sam Hughes wants to know, do the inner rings orbit quicker than the outer rings?
Yes, the inner rings, like if you're in the C ring, it might only take you 4 or 5 hours to go around Saturn once. Out at the F ring, it might take you 14 hours. Just like the planets in the solar system have different lengths of years, so too the rings at Saturn depends where you are, how quickly you get around the planet.
Okay. There are several questions starting to come in about the end of the mission. Now, I will note that we hope that this is only the first of our Facebook Lives about Cassini here at the end of the mission. We plan to discuss the grand finale and the end of mission in more detail at a later time. But folks are really curious about how, what do we expect to see on the last orbit. And you even wrote an engineering paper about it, right, Molly?
Yeah, I did. So the engineering paper I wrote was how we get back that data on that last orbit. So at that very last plunge, so as I described earlier, we turn to Earth, downlink data, and then turn to wherever the spacecraft needs to be for science. But during the final plunge, that last hour or so, we're actually going to be on Earth point the entire time to collect data and immediately send it back to Earth. So we get the last bit of data right before we crash.
So we're going to be talking to Cassini in real time all the way to the very end.
That's right, for the first time in near real time.
Wow.
To watch those data come back, those last precious bits. What's the atmosphere of Saturn, the upper atmosphere, made of? And that's what Cassini's going to tell us in those last moments.
So let's see, for both of you, Wendy Lung Whiteford is asking for her 5-year-old, how long did it take to build Cassini? We built Cassini right here in a clean room at JPL and shipped it to Florida. And how long did it take? That was in 1997 when it launched. How long did it take to build it?
Because I was 5 years old when it was being built.
In 1990, we picked the instruments for the spacecraft, and at that point started to build the instruments and build the spacecraft. We had a few changes along the way. Initially, we had a scan platform and a different configuration, but now we have this sleek machine with everything mounted on Cassini. So it took about 7 years to build it. Launched in 97, 7 years to get to Saturn. And I was there in the late 1980s, and it was a long wait, but boy, was it worth it.
So that, you're talking about your careers. Yours hadn't started when it launched. Your career has, Cassini has been a big part of your career.
Absolutely, absolutely.
A lot of folks want to know, and it's something people always ask, is how could I become a person like you who works as a scientist, an engineer, or any of the hundreds of different kinds of jobs there are working on a space mission? How did you come to have this career that you have? Could you just both talk briefly about how you got here?
Sure. Growing up, I really loved math and science. I really like math because you can figure out an answer and solve something, right? And I remember in high school, I sat on the couch with my mom and we looked at this article that talked about women in STEM fields and how important that was for us to be involved in engineering schools. And I loved space. I was always interested in it as a kid, and it seemed like a great fit. And then when I got into college, I studied aerospace engineering, and I loved every minute of it. And I was so lucky to get an interview at JPL, and I've been here for about 4 years. Yeah.
Well, on the other end of the timeline, I actually grew up and I was a child of the Sputnik era. I got to see the first satellite launched, people walk on the moon. In fact, at one point, I even wanted to be an astronaut. And I had a tiny telescope I pointed up at Jupiter and Saturn. And I loved math and science, took lots of those courses through college. Then I saw this ad in the newspaper after I graduated from college for a job at the Jet Propulsion Laboratory. I went and interviewed, and they said, do you want to work on the Viking extended mission or this new mission called Voyager? And I said, where's Voyager going? And they said, well, Jupiter and Saturn and on to Uranus and Neptune if all goes well. And I said, sign me up. I want to go to the outer solar system. And as the Voyager mission was winding down, after flying by Neptune, I transferred over to Cassini. I'd written my thesis on the rings. And it was such a natural fit to go back to the planet I think has the best ring system in the solar system.
So here's a question from Tabitha Graff that'll lead into our last question. She asked, how long is the day on Saturn? That's a mystery we're still trying to figure out, right?
That's right. We're not sure. It's probably between 10 and 11 hours long. We thought we knew the answer from Voyager, but it's going to take the Cassini end of mission to really try and pin down that answer. So it's probably 10 hours, 45 minutes or so.
So I think we want to get to what's next for Cassini. We want to talk a little bit about what we can expect to see, because as we saw, there's a whole bunch of these orbits left. We're not ending the mission right now. We've got all the way till September 15th is the planned end of the mission. What can we expect to see coming up? What's next, for both of you? Maybe what's exciting for you as well?
I think one of the most exciting things for me coming up is one of our last flybys called T126. It's coming up in a couple of months, and that last flyby really sets us up on that final trajectory as we plunge in to Saturn. So that last flyby sets us up on what's called a ballistic trajectory, and so from that point we could really go hands off on the spacecraft and really just let it go finish its orbits. We're going to do a couple of tweaks with maneuvers, and then it'll end its mission. So that's one of the things that I'm really looking forward to, is that last flyby.
And that's a flyby of Titan,
that's
a giant moon.
Of Titan, a giant moon, because it has lots of gravity to slingshot us where we want to go.
We've used Titan throughout the mission to send Cassini wherever we wanted it to go.
It's a great engine.
Yeah, we've flown by Titan 127 times after that, by that last flyby, using it for that tour engine. That last flyby, we're going to look down at the seas of Titan for the last time at the North Pole, get radar across those, our last pictures of Titan, leap across the rings, and then go into this series of orbits. We'll look at the mass of the rings. We'll look at the interior of Saturn up close in the magnetic and gravity fields. What is Saturn like? How deep do the winds go inside of Saturn? What are the composition of the ring particles? We're going to actually get those D-ring particles into our cosmic dust analyzer. So many questions. And then the pictures. They're going to be great of those innermost rings that we're going to see in exquisite resolution, maybe helping us understand how they formed and how they hang out there and don't just go on into Saturn.
Fantastic. It's going to be great, and so we can't wait. I think that's a wrap for us here at Mission Control from NASA's Jet Propulsion Laboratory. Thank you to both of you. Thank you to everybody who submitted questions online. And if you want to follow along with Cassini here in its final year at Saturn, you can go to the mission website. It's saturn.jpl.nasa.gov. Thanks so much for watching.